Materials can fail in many different ways, and we're going to talk about some of these failure modes today. We've been calculating the load in our truss members and defining whether the member is in tension or compression. And these are two types of failures. If an object is subjected to tension, in other words, pulled in opposite directions, and the stress developed exceeds the strength of the material, it will fail in tension. Similarly, if the object could fail in compression, if the stress developed when compressing the material exceeds the compressive strength. Another failure mode is shear. Shear occurs when you pull on the object in opposite directions. And torsion is when you essentially twist the object like you're wringing out a towel. And then bending is when you take the two ends of the material and pull them down or up. Failure in bending occurs when the moment created by the bending is sufficient to create tension or compressive stresses greater than the yield stress of the material. So to test the materials in tension, we create these dog bone or barbell shaped samples, and then we put them in a load cell with vice grips and slowly increase the load. The reason that we use this dog bone shape is so that the stretch and the failure will be localized in the middle here, not at the grips. We then plot the stress versus the strain for that test. When we do this, we get a plot that looks something like this. That's for a ductile material. There is a lot of information that we can gather about a material from their stress strain curves, including the yield strength, the ultimate strength, the modulus of elasticity, and the toughness, and you'll have the opportunity to plot real data and decipher some of this information for yourself. But for right now, this modulus of elasticity is essentially the slope of the first part of this curve, and it tells us how stiff a material is. So you can imagine how different curves might look like for different materials. In fact, if we do the same test on a brittle material such as a ceramic, the material used to make, for example, your coffee mug, the graph would look very different. The slope is going to be much higher, right, because the ceramic is a lot stiffer. It will not stretch much at all before it breaks. So it's essentially going to go straight up and then break. There's no plastic region. And you can see on the samples on the right how not only does the curve look different, but the samples after they've broken look very different. The ductile sample given on the right here is going to be much longer after testing because it has stretched in the middle, whereas the brittle sample on the left essentially snapped apart without deforming. And then there's the stress strain curve for a polymer, which is a very elastic material. It's going to have a much lower modulus. That slope is going to be a lot smaller. And then obviously a much lower ultimate strength. So it's just going to stretch out and then eventually break. Now, compressive failure occurs when we push or squeeze on a material. If the material is brittle, it will essentially cleave and then break into pieces. A ductile material will tend to smush, and then cracks are going to form on the outside of the material until eventually it won't be able to support any load. We conduct compressive tests by placing the sample between two load cells and essentially doing the same thing as we did with the tensile test, but instead of pulling, the load cells compress the sample, and we measure the load and displacement and then use those to calculate stress and strain to plot. So here are the plots for two materials. Although they look very similar, note the very different stress and strain values for the iron versus the concrete. Shear failure is when we pull on the sample in two different directions. In this example here, we have a bolt that is being sheared by the plates being pulled in opposite directions. The red part is the cross-sectional area of this bolt, and that is the area that is being sheared. And again, we can plot stress versus strain in shear. Here are several examples of setups to test shear strength of material. We can pull apart in this when we put them in vices. Here's a different type of vise. Here we kind of have nailed in and pushing down on one side. We could do it either single or double shear testing. To give an example of the difference between tension and shear, we have two televisions that are bolted, one to the wall and one to the ceiling. The bolts holding up the TV to the ceiling need to have a high tensile strength. They are supporting a load that is pulling on the bolt. In contrast, the bolts holding up the TV to the wall are under a shear load. The bolts holding up these two televisions are subjected to very different loads, and if they fail, their failure mechanisms will be very different. Now here's another visualization of a shear failure. This time it's in a concrete slab. Shear failure is one of the types of failures that will occur in a beam. And this will typically begin with a crack near the supports that then extends out. Another type of failure in beams is a flexural or bending failure. This failure begins with cracks on the edges of the center of the beam. When a beam is subjected to bending, one side will be under compression, and then the opposite side will be under tension. It will fail when the stress is developed on the tension on one side or in compression on the opposite side exceeds the tensile strength or the compressive strength, respectively. To test the bending or flexural strength of material, we place the sample in what we call a 4-point or 3-point bending test. The difference in the test is how many points the load is applied at. The results are also a bit different. The maximum stress in a 3-point bending occurs right under the loading nose, right here. Whereas it is spread out over the area between the two loading nodes in the 4-point bending test. We typically use the 4-point bending test for more brittle materials. Compared to the 3-point bending test, there are no shear forces in the 4-point bending flexural test in the area between the two loading pins. So it's a better test for brittle materials that don't withstand shear stresses very well. The advantage of the 3-point test, however, is that the sample is easier to prepare and to test, but unfortunately, like I said, it is sensitive to loading geometry and strain rate. But if you want a beam to hold loads, you are going to need to have a high flexural strength. So the torsion failure is when an object fails when it's twisted or under torsional forces, which are the result of applied moments that cause shear stress about the axis. A drive shaft is an example of a real object that might fail in torsion. The last type of failure that I want to talk about today is failure in columns. Failure in columns can occur in compression, in buckling, or a combination of buckling and compression, or essentially shear. Compression more likely will occur in short, stocky columns, and buckling will occur more likely in really long columns. We will talk about buckling in columns in a subsequent lesson, but it essentially occurs when the load applied exceeds a critical load that depends not only on the material, but also on the shape and the size of the column. A couple of things I want to point out before we finish is that not all failure is bad. Sometimes we design something to fail, such as this soda can. We want the pop top to come off. Also, there are many different types of failure mechanisms, and we are only touching on a few. In real applications, most objects are subjected to a variety of loads, and so failure can be from a combination of these different loadings rather than from just one type of loading.